Hi, in this video, we will discuss the Fourier series expansion. Previously, you learned how to convert any periodic function into Fourier series format. If the periodic function fx is an even function, then we can further simplify the Fourier series into the Fourier cosine series. If it is odd function, then we can simplify it into Fourier sine series. If the periodic function is not even or not odd function, then we need to use the Fourier series to solve the problem. You must know that the periodic function expressed in terms of the Fourier series, Fourier cosine series, or the Fourier sine series are valid in any interval from negative infinity to infinity. This means that the x variable in these three equations are valid for all the numbers from negative infinity to infinity. In this chapter, we will perform the Fourier series expansion for the non-periodic function. For example, you have a ft function here, which is only valid for a certain interval, from 0 to tau. So this function does not repeat itself over the time. Therefore, we cannot find the period, angular frequency, or the half period information from this function. For a non-periodic function like this, we know that ft will be not equal to the ft plus np. Since this is not a periodic function, therefore we cannot perform the Fourier series on this function. To convert non-periodic function into periodic function, we need to perform the expansion. The first expansion is called the even and odd function expansion. It is also called the full range Fourier series expansion. For example, let the tau to be 4. By using the period equal to tau, then we can expand the original function here and repeat itself over the time. So the solid line here is the original function, and the dashed line here is the expansion result. By using the full range Fourier series expansion, you see we are able to convert the non-periodic function into periodic function through the expansion. This can be done by using the full range expansion, where we choose the p equal to tau. And then you success to obtain the non-periodic function. It's called the full range expansion because you choose the tau equal to the full range of the period. Besides the full range expansion, we can also perform the half range expansion by using this formula. So in this case, you choose the tau equal to half range of the period. This is called the half range expansion. Bear in your mind, the purpose of having the expansion here is to convert the non-periodic function, such as the one here, where you have finite interval from 0 to tau. So in this case, our tau is equal to 4. After you perform the expansion, such as the full range expansion or the half range expansion, then you can convert it into the periodic function. Then we can continue to find the Fourier series result. So this is called the Fourier series expansion strategy. Bear in your mind, without the expansion here, then we can only use the Fourier series for periodic function. For the non-periodic function, then you need the expansion technique to convert the non-periodic function into periodic function through the full range or half range expansion. With that, you can obtain the Fourier series expansion result. So we choose the p equal to tau for full range expansion, and the tau is equal to 4 in this case. So substitute p equal to 4 inside this formula, you obtain angular frequency equal to pi over 2. Full range Fourier series expansion is given by this formula. If you compare to the previous Fourier series formula, then you found they have the similarity. Since the function is in t variable for this signal, we replace all the x variables to be the t variable here. When you compare it side by side, you see you have the same formula for the ft function here. It has a constant a0 plus the cosine term and the sine term. The formula to compute the coefficient a0, an, and bn are also the same. The main difference is we change the lower and upper limit to be from 0 to tau. Previously, we learned that we must select the ft to be within one period. The same rule is applied for the full range Fourier series expansion. For the full range expansion here, we assume the function ft is within one period from 0 to tau. Therefore, we need to integrate from 0 to tau for the full range Fourier series expansion. The main difference between the Fourier series and the full range Fourier series expansion is the ft function that is obtained by the full range Fourier series expansion is only valid for certain interval from 0 to tau. On the other hand, the ft function obtained by the Fourier series is valid from negative infinity to infinity. Besides full range expansion, we can also perform the half range expansion by taking the half range of the period t over 2 equal to the tau. So we have a function here that is valid only for certain interval from 0 to tau. Let the tau equal to 4 for this example. So we can't perform the Fourier series on this signal because it's a non-periodic function. So we need to perform the half range expansion, such as this case, to convert the non-periodic function into periodic function. By performing the half range expansion, you have your p over 2 here to be equal to the tau. Then one period will be from negative 4 to 4. Then it expands and repeat this function over the time. The question is, what is the function from negative 4 to 0 here? So you have learned even function previously, where the y-axis is like a mirror. You will copy your right hand side data into the left hand side. If you assume this is one period, from here to here, then the signal will repeat itself over the time. So we can expand this function in this way. So you have one period, this is another period, this is the next period, and you can keep continuing. So we are actually doing the even function expansion, and this is the result. Since the period is equal to 8 in this case, substitute inside this formula 2 pi divided by 8, you obtain the omega equal to pi over 4. Besides assume this part to be even function, we can also assume this part to be odd function. For the odd function, then you have the y-axis to be the upside down mirror. So on the right hand side, you have the signal to be this. Rotate the signal 180 degrees, then you will obtain the odd function. Since this is one period, from here to here, expand this signal, then you can obtain a periodic function like this. So this is called the odd function expansion, and you should get this result. Same, you have the half period p over 2 is equal to the tau. So the period here is equal to 8. Then you can obtain the omega equal to 2 pi over p, which is pi over 4. So we have three types of expansion which can be used to represent the non-periodic function in the Fourier series format. First of all, you have the full range Fourier series expansion, where the function after expansion is not even or odd function. It is combination between even and odd function, where the even function consists of the constant a0 and the cosine term here. Odd function is represented by the sine term here. We can also perform the half range expansion by using the even function expansion to obtain this result, and odd function expansion to obtain this result. We know that for the even function, you don't have the sine term, therefore your bn will be equal to 0. So in this case, we call it as the half range Fourier cosine series expansion, and the ft is equal to a constant a0 plus the cosine term. For the odd function, you don't have the constant and the cosine term, therefore the a0 and an here will be equal to 0. Of function expansion is also called the half-range Fourier sine series expansion, where you only have the sine term. You need to be careful. For the half-range expansion, the period is different with the full-range expansion. So for the full-range expansion, we let the tau equal to the full range of the period, and for the half-range expansion, we let the tau equal to the half range of the period, which is p over 2. Since the period is different, therefore the omega that you obtain is different as well. So when you substitute inside this equation, so you need to be careful. These two omega are different if you use different expansion method to solve the problem. When you compare the coefficient that we use to compute the A0 and the AN here, you see the constant is different here. It is 2 times larger than the full range expansion formula. Same to the Bn formula here, where you can see the constant here is larger than this constant, and you need to multiply 2 to obtain this formula.